Hello everyone, welcome back to my lecture series on fluid mechanics and hydraulic machines. We are continuing our topic of viscous flow. In our previous lecture, we studied about flow of viscous fluid through a circular pipe. We obtained the shear stress distribution, velocity distribution and ratio of maximum velocity to average velocity. Now we will move forward with this and calculate drop of pressure for a given length. So first let's copy this figure onto our virtual board. So our theory is drop of pressure for a given length. So here we will continue with the equation of average velocity, that is u bar is equal to minus 1 upon 8 mu del p over del x into r square. So here we can get the negative value of del p over del x is equal to 8 mu u bar divided by r square. Now to obtain the value of drop of pressure, we will integrate this. That is here we can still write down this minus dp is equal to 8 mu u bar over r square dx. So here to integrate this from 2 to 1 here and here, so what we will be getting here is minus of u1 minus p2 is equal to 8 mu u bar divided by r square into x1 minus x2. So here P1 minus P2 is equal to 8 this L is coming? Because here in this figure, the difference between x2 minus x1 is L. Let me write down over here that actually x2 minus x1 is equal to L. So that's why we are getting this. And now instead of R we can put B upon 2. That is, we can put instead of R square is equal to B square upon 4. So finally we will be getting P1 minus P2 is equal to 32 mu U bar L upon D square. And we can also write down P1 minus P2 upon rho G is equal to 32 mu U bar L upon rho G D square. So that's all we have as a drop of pressure here, pressure here. So this is also known as Keval. So let's copy this work into our main slides. So that's all we have for this theory, and now we will move forward with our next theory that is the flow of viscous fluid between two parallel plates. Now if you see here, instead of a circular pipe we are having fluid between two parallel plates with fluid being viscous. So in this figure we have two parallel plates, and here this is the y direction, and here horizontal is x direction. The thickness, the gap between two parallel plates is small t. We are considering an elementary volume having x dimension as delta x and y dimension as delta y, and the third dimension, which is perpendicular to your screen, is taken as unity, and the distance of this element from this bottom parallel plate is small y. Here similar to previous theory, we are having the two forces. First is pressure force and second is shear force. So pressure force on surface on face AB is P into delta y into 1, because here, for let us say if we discuss about face AB, then it will look like this. So this will be the entire face, where this will be delta y and this will be 1. So here the area, that's why is delta y into 1, and similarly the pressure force on face CD will be P plus del P over del x delta x into delta y into 1. So these two are the pressure forces, and as far as the shear force is concerned, on face CB, it is delta x, and this will be 1, that is perpendicular to the screen. That's why here the area where shear force is acting is delta x into 1, and for the face AD it is tau plus del tau over del y delta y. This will be the total shear stress into area on which the shear stress is acting is delta x into 1. So that is the shear force and pressure force acting on this element, which is between two parallel plates, and the fluid flow is from left to right, and the fluid is viscous. So now let's copy this figure onto our virtual board, that is over here. I hope this will be just fine. And now let's move forward with our analysis. So here again the resultant force in x direction will be 0 under equilibrium condition. So plus P here, under equilibrium condition, the forces in x direction will be summation of forces of x in x direction will be 0. So plus p into delta y minus p plus dp over del x into delta x into delta y minus tau into delta x plus tau into tau plus del tau over del y into delta y delta x is equal to 0. So here few parameters will get automatically cancelled, so we will not focus on them. So finally what we will be getting here is, I am directly writing down dp over del x into delta x to delta y is equal to del tau over del y into delta x into delta y. So finally what we are getting here is del p over del x is equal to del tau over del y. Now we should focus on the velocity distribution. So for that purpose we will continue from here itself, that is del p over del x is equal to del over del y into mu into mu upon dy is equal to mu into square. So finally what we have obtained is del p mu upon del y square is equal to 1 upon mu into del p over del x. Now we will be integrating this. So what we will be getting here is del u over del y is equal to 1 upon mu del p over del x into y plus c1, and here we will maintain the value of u for the second integration, which will give us 1 upon mu into del p over del x into y square upon 2 plus c1 y plus c2. That is the value of p. Now we need to evaluate the value of c1 and c2. For that we will require the boundary conditions. So here if you see this figure, then to obtain the boundary condition, two situations is there. At y equal to 0 the velocity will be 0, as well as at y equal to t, that is at the upper plate, u will also be 0. That is, at two locations we are having velocity being 0. First at the bottom surface, that is y is equal to 0, and second is at the top surface where y is equal to t. So here at y is equal to 0, u is equal to 0. That is the first boundary condition. So what we will be getting here is the value of c2, which will be 0. You can check it by yourself that the value of c2 is 0 when you put it over here. Now second boundary condition, at y is equal to t, u will be again equal to 0. So for that we can say that 0 is equal to 1 upon mu into del t over del x into here we are getting the value of C1 is equal to minus 1 upon 2 mu into del P over del X into T. So that is the value of T that we have obtained, the value of C1 we have obtained. So finally what we will be having here is U is equal to 1 upon mu del P over del X y square upon 2 minus 1 upon 2 mu del P over del X into T. So here ultimately what we are getting is value of U is equal to minus 1 upon 2 mu. We are missing something, that is this minus 1 over 2 mu del P over del X into Ty minus y square. That is the final value of velocity. So we have obtained the velocity distribution also, and now we can copy this work into our main slides. Now we will see the shear stress distribution. Let me see if we have enough time. No, we will be continuing this topic into our next lecture. So let me quickly go through what we have done till now. So we begin with flow of viscous fluid through a circular pipe, that is over here. We obtained the shear stress formula and velocity formula, and based on those two formulas we understood the distributions. Then we obtained the ratio of maximum velocity to average velocity, that is twice u max upon u bar. Then we obtained the Hagen-Poiseuille's formula, that is drop of pressure for a given length. Then flow, we studied about flow of viscous fluid between two parallel plates. Here we obtained the formula for velocity distribution. So that is the end of today's lecture. Thank you for watching this video.